Hello, and welcome to this second presentation related to calculating volumes using standard formulae. This is part 2 of this lecture. Here we're going to consider slightly more complicated formulae, such as the spherical cap, shown here, the frustum of a cone, shown here, and also the frustum of a square-based pyramid. This presentation does assume you've seen part 1 of this lecture. Let's start by considering the spherical cap, diagrammatically shown here. But let's first consider a practical illustration of where a spherical cap is used. For example, considering this road tanker, often the storage area of the tanker has slightly domed ends, shown here, and these are essentially spherical caps. It should be noted that sometimes these spherical caps are actually in the form of hemispheres, so they're hemispherical ends. And hemispherical ends, which is of course half of a sphere, as we reviewed in our previous presentation, are used when you have high internal pressures within the storage container itself here. Consider the spherical cap, shown here in the sketch. The volume V of a spherical cap is given as pi multiplied by h squared, where h is the height of the spherical cap, and that's multiplied by, in brackets, 3 multiplied by uppercase D, which is this diameter here, minus 2 multiplied by the height h. And it's all divided by 6. So that's the formula for the volume of a spherical cap given without proof. If we want to calculate the curved surface area of the spherical cap, so the area of the dome effectively, then the formula is given as pi multiplied by diameter uppercase D multiplied by h, again given without proof. Let's consider an example. A spherical cap of a pressure vessel has a diameter uppercase D of 1.22 meters and a depth or height h of 300 millimeters. We've got to calculate the volume of fluid in litres that will be contained within the cap. Extracting information from the question, diameter D is 1.22 meters. Notice that the depth or the height of the spherical cap h is 300 millimeters in the question. And I've converted that to meters here, 0.3 meters. So from above, the volume of the spherical cap, V, is given by this equation. It's written on one line here. And inserting the values of h and uppercase D into the equation, we can determine the volume, and that's 0.1442 meters cubed. Just note the question wants us to state the volume in terms of litres, so V in terms of litres, we would have to multiply 0.1442 by 1,000. There are 1,000 litres in 1 meters cubed, so the volume is 144.2 litres. Exercise 1S. A spherical end of a pressure vessel has to accommodate a capacity of 290 litres. The depth of the cap is 35 centimeters, and we're asked to calculate the diameter, uppercase D, in the equation, from which the cap has to be made. The answer is given here in the bracket. I've just shown for reference the formula for the spherical cap from the previous slide. I would encourage you to start the presentation and attempt exercise 1S. It will involve transposing this equation to find uppercase D here. I will show you the full work solution on the following slide. Exercise 1S, here's the solution. So extracting the information from the question, the spherical end cap has to accommodate a capacity of 290 litres, so the volume is 290 litres. That's been converted here into meters cubed, so that's 0.29 meters cubed. Remember, there are 1,000 litres in 1 meters cubed, and the depth or the height of the cap is 35 centimeters. So the depth h here, shown here on the sketch, is 35 centimeters, and divided by 100, that's 0.35 meters. Remember, there are 100 centimeters in 1 meter. The question wants us to calculate the diameter capital D, and that's shown here in the sketch. So knowing the volume of a spherical cap, V, is given by this equation here, what we need to do is transpose the equation to make the diameter the subject. So rearranging, firstly we multiply both sides by 6 to obtain 6V on the left hand side. Next we divide both sides of the equation by pi h squared. Then we add 2h to both sides, and then we divide throughout by 3. So dividing both of these terms here by 3, the first term divided by 3, so that's 6 divided by 3 is 2, and the second term is divided by 3. That's now equal to diameter D. Noting that 2 is a common factor on the left hand side of the equation, we can state the final equation for diameter in this form here, with a common factor of 2. Inserting our values from above, the volume V is 0.29, the dimension h is 0.35, and evaluating diameter capital D is 1.74 meters. Let's now consider the frustum of a cone. So the frustum is a portion of the cone, or of a pyramid, we'll see that formula in a moment, between the base and a horizontal slice which removes the pointed portion of the cone. So in other words here, this slice here. The volume formula is given as shown here without proof. It's pi multiplied by the vertical height h, and in brackets we now have the bottom diameter squared, that's uppercase D, added to the bottom diameter multiplied by the top diameter, that's lowercase d here, and then we add the lowercase d squared. And that's all divided by 12. So that's the volume of the cone formula. To work out the total surface area, that's combined of the curved surface area, AC shown here, and that's pi multiplied by L, which is the slant length shown here, and multiplied by, in brackets, the bottom diameter added to the top diameter, and it's all divided by 2. The surface area of the ends, top and bottom ends, I've called that. Obviously there are 2 areas to consider here. Using our standard formula for the area of a circle, that's pi uppercase D squared divided by 4, so that's the area of the bottom of the cone, and we add to that pi multiplied by the top diameter squared divided by 4. Just be careful here that in the curved surface area formula we need the slant length L, so to work out the slant length or height L here, we use Pythagoras' theorem. So to calculate dimension L, shown here, it will essentially be this dimension here of a right angled triangle, the bottom diameter minus the top diameter divided by 2 all squared, added to the height squared. In other words, this dimension here. So that's how we calculate length L. Here's an example. A concrete column is shaped in the form of a frustum of a cone having a height of 2.8 meters. The diameter of the top is 1200 millimeters. The diameter of the base is 1800 millimeters. Reading the question, we got to calculate the volume of concrete in the column in meters cubed and the curved surface area in meters squared. So here's our solution. So first of all, calculating the volume. We're given in the question the height is 2.8 meters. And notice the top diameter has been converted from 1200 millimeters into meters here. and so is the bottom diameter. That's converted into 1.8 meters. Here's the volume formula from the previous slide, written on one line here. I just simply insert the values into the formula. The height, h, is 2.8 meters. The bottom diameter is 1.8 meters. And the top diameter is 1.2 meters. Evaluating my volume is 5.01 meters cubed. To calculate the curved surface area only here, so my area formula from the previous slide shown here, written on one line. Notice I have to calculate the length L, slant length. This dimension will be 0.3 squared. Here's the 0.3, which of course is this side of the triangle here. And we add that to the height squared, 2.8 squared. H is 2.8 here. That's obviously this side of our triangle. So evaluating the slant length L is 2.816 meters. Inserting that into this equation now, we've got pi multiplied by the L. Then in brackets we've got the bottom diameter D, shown here, added to the upper diameter, lowercase d here, and all divided by 2, of course. Evaluating the area of the curved surface is 13.27 meters squared. That's an illustration of calculating the volume of the frustum and also the curved surface area only. Let's consider the frustum of a pyramid. The volume formula shown here, V is equal to the height h of the frustum. And then in the bracket here we have the area of the base, area of the bottom here, and that's added to the square root of the area of the base multiplied by the area of the top shown here, and then that's added to the area of the top, and it's all divided by 3 here. The total surface area, A here, is the area of the top added to the area of the bottom, and then we add to that the summation of the areas of the trapeziums that form the sides. These are trapezium shapes shown here, and there are 4 of them. Let's consider an example. So a square cross-section casting has a height of 2 meters. The casting tapers uniformly along its length from a square, having a side length of 200 millimeters at one end to a length of 100 millimeters at the other. In other words, from the bottom to the top as shown in the diagram. We've got to determine the casting's volume here. So extracting information from the question, uppercase B, the length of the bottom of the pyramid here is 200 millimeters. I've converted that to meters, 0.2 meters. The length of the top, that's lowercase b, is 100 millimeters in the question. Converted that to meters, 0.1 meters. And the height in the question is given as 2 meters. Here's our equation for volume, as stated above, but here written on one line instead of 2 lines. Note the area of the base is calculated by b multiplied by b because it's a square cross section, so 0.2 multiplied by 0.2, so 0.04 meters squared is area of the base, and the area of the top is 0.1 multiplied by 0.1, so 0.01 meters squared. Inserting the areas into the equation above, knowing the height is 2 meters, we can evaluate the volume, which is approximately 0.0467 meters cubed. Let's consider some examples from our worksheet B. These relate to volumes and surface areas of various standard sections. I'll outline the questions here, but I'll just work through selected solutions on the following slides. So question 1 is a small cone in this case. We're given the maximum diameter of the cone, we're given the vertical height of the cone, millimeters here. We've got to calculate the volume and the total surface area. That's the type of question we reviewed in the part 1 presentation on calculating volumes. I'll let you review that at your own pace. The answers are given in the bracket. Question 2 is a cement silo in the form of a frustum of a cone. Here's a picture of a cement silo, and this is the frustum of the cone, sometimes termed the hopper section. So the hopper is idealized as a frustum of a cone. We're given its height, which is 3 meters, given the diameter at the top, which is 2.4 meters, and the diameter at the bottom, which is 1.2 meters. We've got to calculate the volume of the cement that this will hold. Also, we've got to find the total surface area, assuming the frustum had a top and a bottom. Answers shown in the bracket again. And question 3, a metal bucket 400 millimeters deep. Its diameter at the top is 300 millimeters. Its diameter at the bottom is 200 millimeters. We've got to calculate the number of liters of water that the bucket will hold, assuming that it's a frustum of a cone. Again, the answer shown in the brackets here. I'd encourage you to start the presentation and attempt these questions, but I'll show you a solution to question 2 on the following slide. Here's question 2 solution relating to the frustum of a cone. Extracting the information from the question, the vertical height is 3 meters, shown in my sketch here. The maximum diameter, uppercase D, is 2.4 meters, shown here. And the minimum diameter, lowercase d, is 1.2 meters, and that's shown here. Part 1, I'm calculating the volume V. Here's our volume formula that's been given on the previous slide. Inserting the values from above for the height. Here's the maximum diameter, uppercase D, the minimum diameter, lowercase d. So evaluating the volume is 7.92 meters cubed. Question 2, solution continued for our frustum of a cone. This is part 2. We're finding the total surface area of the frustum here. I've just repeated the geometry given in the question from the previous slide, and I've also sketched a diagram again of the frustum. So to find the curved surface area, first of all, go to A1 here. Here's our formula. It's pi L multiplied by, in brackets, the large diameter added to the small diameter. It's all divided by 2. We need to calculate the slant length L here. So L is calculated from Pythagoras' theorem, shown here. Notice that the x dimension is this dimension here, calculated from the geometry. And of course h is the height, which we're given in the question. So evaluating the slant length or slant height, that's 3.0594 meters. We can now put that into this formula for A1, here it is, and inserting the large diameter and the small diameter into the equation. And evaluating A1 is 17.3 meters squared. Calculating now the area of both ends, the area at the bottom and the area at the top. Put this A2 here. The area at the bottom here is pi multiplied by the large diameter squared divided by 4, and the area at the top here would be pi multiplied by the smaller diameter squared divided by 4. So evaluating A2, area of both ends, is 5.655 meters squared. So total surface area A is the A1 plus the A2, so the area is equal to 22.955 meters squared. Questions continued here. In question 4, we're required to replace 2 pipes having bores, that's internal diameters, of 28 millimeters and 70 millimeters, with a single pipe that has the same area of flow, same cross-section area basically. We've got to find the bore, the internal diameter of this single pipe. So essentially you have to calculate the area of the 28mm bore and then the area of the 70mm bore, add them together. Then using the appropriate formula, you have to find the diameter of a single pipe that has the same combined area. I'll let you review that at your own pace, but the answer is shown here in the bracket, but notice it's in centimetres. Question 5 is a pyramid, has a square base of side 2 meters and a height of 4 meters. You've got to calculate the volume and the total surface area. Again, that's a question similar to what we reviewed in the previous lecture on using standard formulas. Question 6, a bucket that's used on a crane is in the form of a frustum of a pyramid. Its base is square of 600mm side length and the top is also square 750mm side length. Depth of this bucket is 800mm. There are two parts to the question. Part A, we have to calculate in cubic meters the volume of the cement that the bucket will hold. And part B, if 20 of these buckets of cement are emptied into a cylindrical cavity having 4 meters diameter, we've got to calculate the depth to which the cavity will be filled. So question 6 is a slightly thought-provoking question. The answers are given here in the bracket again. I would encourage you to stop the presentation and attempt these questions, but I will show you the full solution to question 6 on the following slides. So question 6, our bucket is in the form of a frustum of a pyramid. I've shown the bucket upside down effectively here just to keep it in line with the standard equations that we've been using. So in our case, the bucket base dimension is actually 0.6 meters, so this is 0.6 here, and the top dimension, lowercase b here, is actually 0.75 meters, so this dimension 0.75. But as I said, I'm just keeping the diagram in the form given in the standard equation on the previous slide here. The depth or the height of the bucket h is 0.8 meters. So that's the information extracted from the question. So question 6 continued. This is part A here, and we're calculating the volume. To calculate the volume of the frustum, here's the volume formula shown here. We need to calculate the area of the base. So in this case, the area of the base would be 0.6 squared, given B is 0.6. And the area of the top is 0.75 squared, which equals 0.5625 because our top dimension is 0.75 meters. Inserting the values into the equation shown here, noting that the height is 0.8 meters, we can evaluate the volume of the frustum. It's 0.366 meters cubed. In question 6 continued, this is part B here. Part B, we have to calculate the depth to which the cylindrical cavity is filled. So now we're considering this shape, a cylinder that's being filled with the concrete. We're told in the question that 20 of the buckets of cement are emptied into this cylindrical cavity of 4 meters diameter. Our diameter here is 4 meters. We've got to calculate the depth to which the cavity will be filled. So the volume of 20 buckets will be 20 multiplied by the volume calculated on the previous slide, which is 0.366 meters cubed. So 20 multiplied by 0.366 is 7.32 meters cubed. That's the total volume of concrete that will be pouring into this empty cylindrical cavity. So knowing the diameter D is 4 meters, knowing the volume formula for a cylinder is pi d squared h divided by 4, we can rearrange the equation to find the depth or the height h. And rearranging this equation, that becomes 4 multiplied by the volume of the concrete divided by pi multiplied by d squared. So inserting the volume of 20 buckets calculated above, inserting the diameter, which is 4 meters in this case, we can calculate the depth or the height to which the cavity is filled, and that's 0.5825 meters. That's height h here. Here's the bibliography used to help generate this presentation, and I hope this has been of interest to you, and thank you for viewing.